We have a straightforward test for determining whether or not an alternating series converges. It turns out that convergent alternating series can be used to approximate known values like the cosine of an angle, or the natural log of 2, or e to some power. When we use them in this way, it's often helpful to know how close our estimate is to the actual value. Here we're going to talk about a straightforward technique for finding the bound on the error estimate when we use a partial sum to estimate an alternating series. Let's start off with some definitions and notation. We're going to consider the sum from n equals 1 to infinity of negative 1 to the n plus 1 times a sub n in two pieces, s sub n plus r sub n, where s sub n is the nth partial sum, and r sub n then represents the remainder or the maximum possible error that we would find when we estimate our sum using the nth partial sum, s sub n. To understand how we might find a bound for the error, let's take a look at a convergent alternating series. Here we can see that our sequence of partial sums begins to converge around the value of this series. The value of the series is indicated by the purple line in the animation above. Notice that as we take more and more partial sums, they get closer and closer to this line. This means that the area that falls above and below the line for any given partial sum is the maximum amount of error that is left in the series when calculating that particular partial sum. The orange bar in our image then represents the maximum value for the remainder for the nth partial sum. In other words, the height of that bar is going to be our value for r sub n. We can see then fairly easily that r sub n is no bigger than the difference between the nth partial sum and the n plus first partial sum. We also know that the difference between the nth partial sum and the n plus first partial sum is just the n plus first term of the series. Putting these ideas together, if we break up our series into the nth partial sum plus the remainder, then we know that that remainder is less than or equal to an plus 1, the n plus first term of our series. We know the alternating harmonic series converges. It turns out that the value it converges to is the natural log of 2, which means that we can use that series to approximate the natural log of 2. Let's use our error estimate in order to figure out how many terms we would need in order to estimate the natural log of 2 to within 1/1000th of its actual value. Our formula tells us that any error estimate is going to be less than or equal to the an plus first term. In this case, that term is 1 over n plus 1, and we want our error to be less than 1 over 1000, 0.001. That is equivalent to saying that n plus 1 must be greater than 1000, which means that n must be greater than 999. So to estimate the natural log of 2 to within 0.001, we need to use s sub 1000. Like the natural log of 2, we can also use an alternating series to estimate the value of e to the negative 1 power. It turns out that e to the negative 1 is equal to 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial, and so on and so forth. So our mission here is to use 4 terms to estimate e to the negative 1, and then find a bound for the error on that estimate. Using 4 terms to estimate this is fairly straightforward because we can see the 4 terms in front of us. We know that e to the negative 1 is going to be approximately 1 minus 1, and that's not a typo. That is, in fact, the correct beginning to this series, plus 1 over 2 factorial minus 1 over 3 factorial. Those are our first 4 terms. Well, that is the same as 0 plus 1 over 2 minus 1 over 6. 3 factorial is 3 times 2. So we have 3/6 minus 1/6, which is 1/3. We can see that using 4 terms, we get that e to the minus 1 is approximately 1/3. Now, our error estimate, r sub 4, has to be less than or equal to the 5th term, which is going to be 1 over 4 factorial, which is 1 over 4 times 3 times 2, which is equal to 1/24. Our error estimate, 1/24, is approximately equal to 0.04. We also know that 1 over e minus 1/3, using a calculator, that difference is 0.0345. 1 over e is my calculator is telling me that that is about 0.3679. And we can see then that our error estimate was in fact larger than the actual error that we got when we compared the value of 1 over e to the value we got using the fourth partial sum. Wrapping up what we know. If we have an alternating sequence that converges and its terms do not increase in magnitude, then we can split that series up into the nth partial sum plus the nth remainder. So that remainder, the series minus the nth partial sum, is no bigger than the n plus first term of the series itself.